Hello and welcome back to the video for lesson 7.4. We are going to work on confidence intervals and sample size for proportions. And we use proportions when we have qualitative data. So it's important to remember when we have quantitative data, it's numerical, usually something measured, because if it was counted, we would be using the binomial distribution. But when it's quantitative and measured, we're talking about means, and that's lesson 7.3. But now we're talking about qualitative data and proportions. So we have to know some of the little pieces and parts. The p hat is equal to the x divided by n. It's the estimated proportion of successes. The p hat is a point estimate for p, the true proportion. So we're estimating the true proportion. X is number of successes, n is the sample size. The margin of error for a proportion is found by taking the critical z. Now notice we used a critical t in lesson 7.4, but for proportions we use a critical z. So that's important. And to find the critical z, we only need to know the alpha divided by 2. And then that's going to get multiplied by the standard error that we learned about earlier in chapter 7, which is this, or actually in chapter 6. From the central limit theorem, is the square root of p hat times q hat divided by n. And remembering that q hat is the same as 1 minus p hat. And then we would say the percent confidence interval to estimate the population proportion is the p hat minus this margin of error, or the p hat plus this margin of error. Now, there is a Desmos link here because there's a Desmos program which is going to help us a ton. And the things that you need to know about the Desmos program is that you will have to enter the n, which is the sample size, the p, which is the sample proportion. So you need to know that. You can't just enter x and n. We don't need p0. That will be used in chapter 8. We do need to know the alpha. Or you can type in 1 minus the confidence level. And then you're going to click on the drop down for the confidence interval, and then you'll have the lower boundary for your interval and the upper boundary. So the first example I have done for you here in the notes so that you can just follow along. Suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. 500 randomly selected adult residents in this city are surveyed to determine whether they have cell phones. Of the 500 surveyed, 421 responded yes. So of the 500, 421 responded X. So that's down here. Our sample size is 500 and the number of successes was 421. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of adult residents of the city who have cell phones. So our alpha is equal to 1 minus the confidence level. So 1 minus the confidence level is 0.05, and alpha divided by 2 is 0.05. And we are going to remind ourselves that to find this z of 0.05, we're going to use the inverse CDF of the normal dist. We've been using this for a while, with mean 0 and standard deviation 1, comma 1 minus 0.025. And that gives us a rounded of 1.96. Now our sample p hat, the sample proportion or point estimate, is x divided by n, so that 421 who said yes, they have a cell phone out of the 500 is 0.842. Now, the rest of our EVP, or margin of error here, is our critical z multiplied by the square root of p hat times q hat divided by n. And there's our p hat and our q hat. Remember that q hat is 1 minus p hat. So they add to make 1 divided by 500. This all has to be inside that square root. So the margin of error is 0.032. So to find our lower and upper boundaries of the confidence interval, we take our p hat and subtract our margin of error, and then our p hat and add our margin of error. And then we have our interpretation. We estimate with 95% confidence that between 81% and 87.4% of all adult residents of this city have cell phones. Suppose 250 randomly selected people are surveyed to determine if they own a tablet. Of the 250 surveyed, 98 reported owning a tablet. So let's define X and P. So X is the number of people who own a tablet, and P hat is the proportion who own a tablet. Which distribution should you use for this problem? And we're going to use the Z distribution because we're talking about proportions. Calculate the P hat. So the P hat is the 98 divided by 250. And we're going to go ahead and go to Desmos. And I'm just going to look at that 98 divided by 250. So our P hat is 0.392. And you can see that here, I calculated it. I also calculated our critical Z because alpha is 1 minus 0.95. And so alpha divided by 2 is 0.05 divided by 2, which is 0.025. And right here, so I'm just showing you that the Z for 0.025 is 1.96. And then our margin of error is 1.96 multiplied by the square root. You can see that here in the Desmos, divided by the sample size of 250. And so our margin of error is 0.0605. And you can take the P hat and subtract that whole margin of error. And I just subtracted the whole calculation because then I know it's more accurate. And then I took the 0.392 and I added that whole calculation. So our interval is 0.3315 rounded to 4 decimals up to 0.4525. Now I'm going to show you the Desmos program. It is saved in Canvas. You can grab that. It's called the confidence interval for proportions, one sample. We're going to put in our sample size of 250 and our proportion. The more decimals you put in, the better, because it's more accurate that way. We don't need the P0. We do need our alpha, which is 0.05. And then we can go down to our drop-down menu for confidence interval that's open. And it verifies that our lower boundary is 0.3315 and our upper boundary is 0.4525. Then we can do our interpretation, which is important. So we can say we are 95% confident that the true proportion of people who own a tablet is between, I'm going to put it in percentages, or you can leave it as a because I said proportion. If I said the true percentage, I would turn it to percents. I said true proportion, so we can leave it as decimals. 0.3315 and 0.4525. Let's look at example 3. For a class project, a political science student at a large university wants to estimate the percent of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. X is the number of registered voters, and P hat is the proportion of voters from sample. We're both from the sample, but X is the number, so that gives you 300. P hat is the proportion out of the 500. What distribution do we use? Again, we use the Z, and our P hat is equal to 300 out of 500, which is 0.6. Compute a 90% confidence interval for the true percent of students who are registered voters and interpret the confidence interval. So that means alpha is 1 minus 0.90 or 0.10. And alpha divided by 2 is 0.10 divided by 2 or 0.05. So we need a critical Z of 0.05. Go back to decimals. And our voters here, there's our critical Z value. It's going to be, it says a negative 1.645, but remember, if we do 1 minus, it gives us a symmetric positive 1. So either way, we're using the positive 1 in the calculation. And I round mine to 3 decimals, 1.645. And our margin of error is calculated there. 1.645 times the square root of P hat times Q hat divided by the sample size of 500. And so our margin of error is 0.0360. And then we take our P hat, which is 0.6, and subtract that margin of error and add the margin of error. And again, we get the lower boundary of 0.5640 when rounded and 0.636. And we can go to our program just to verify this. It's good to do it by hand a few times, and then just going to the program works just as easy. So 500, our sample proportion. And if you're not sure of the sample proportion, you can type in 300 divided by 500, and it calculates that 0.6 for you, which is nice. We don't need the P0, but this time our alpha is 0.10. And then we go down, and there is our lower boundary and our upper boundary, just as we had calculated. And then we can go ahead and explain your interpretation. So this time we're 90% confident that the true percent of students who are registered voters is between, and because I said percent, I'm going to turn it into a percent. So it's up to you. I think Alex is probably going to use the decimal version. So 56.4% and 63.6%. Let's look at example 4. So example 4 says a student polls his school to see if students in the school district are for or against the new legislation regarding school uniforms. She surveys 600 students and finds that 480 are against the new legislation. X is the number who are against the legislation, and P hat is proportion against legislation. And we're still using the Z distribution, and the P hat is 480 out of 600. And we're using 90% confidence, so that means our alpha is 1 minus 0.90 or 0.10, and that's what we're going to use for Desmos. So let's just go ahead and go to Desmos and check it out. So our P hat is 0.8. And we know from before that our critical Z is 1.645 from the last problem. And we can just go to our computer program here and type this in just as easy. So we have 600 in our sample. And our P hat was 480 divided by 600. There's our P hat 0.8. And there's our alpha. And we can just go straight down to our lower and upper boundary. And the confidence interval is 0.7731 to 0.8269. Margin of error. And we don't really need it here because we used a computer program to find it. So let's look at the last example of the confidence intervals, and then we're going to go to some sample size problems. So it says in 6 packages of the Flintstones real fruit snacks, there were 5 Bam Bam snack pieces. The total number of snack pieces in the 6 bags was 68. We wish to calculate a 96% confidence interval for the population proportion of Bam Bam snack pieces. Let's look at what X and P hat are. So X is the number of Bam Bam pieces and P hat is the proportion of all pieces that were the Bam Bam shape. And we're using the Z distribution. My P hat is the 5 that were Bam Bam out of 68 pieces that were total in all the bags. We want a 96% confidence interval this time, so we're jazzing it up a little bit here. So my alpha is 1 minus 0.96 or 0.04. My alpha divided by 2 is 0.02. So I need a critical value for Z of 0.02. And we're going to go ahead and use the computer program to find that. And there were 68 total pieces. 5 of the 68. So there's my sample p hat is 0.0735. And then my alpha is 0.04. And so my lower and upper boundary are right here. Which is my lower boundary is 0.0085 and my upper is 0.1385. And the last question on the paper says, do you think that the 6 packages of fruit snacks yield enough data to get accurate results? Why or why not? And I would think that that might have to do with the sample size. So to be able to use the central limit theorem, we have to prove that it's normal. And in order to do that, NPQ has to be greater than or equal to 10. And in this case, they were only N was 68 bags, or 68 pieces, I mean. And P hat is 0.0735, and 1 minus P hat is 0.9265. So let's just make sure. If we look at that. We can say 68 times. And so that is not bigger than 10. That is only 4.63, which is less than 10. So I would say that it's definitely not normally distributed, and we really shouldn't be using the central limit theorem to predict this. We should really be using more than the 68 pieces. So more than the 6 bags for sure. So let's look at calculating sample size. Okay, so we are going to talk about sample size for proportions in this lesson, end of this video here. It says if researchers desire a specific margin of error, then they can use the error-bound formula, the margin of error, to calculate the required sample size. The error-bound formula for a margin for a population proportion is the sample size n should be the p hat times the q hat times the critical z divided by the margin of error. And that's z of alpha divided by 2. This is if you already have a prior estimate for p hat. So let's say you did a sample last year and you had a certain sample size, and so you kind of know that what the p hat was from the last year. If you don't have a prior estimate p hat, then in order to find n, we need to know the estimated sample proportion, p hat. Remember that q hat is equal to 1 minus p hat, but we do not know p hat yet. Since we multiply p hat and q hat together, we can make them both equal 0.5. And so in that case, p hat times q hat equal to 0.5 times 0.5 is 0.25, would result in the very largest possible n, because if you made p hat up to 0.6, then q hat goes down to 0.4 and you get 0.24. So the very maximum that p hat and q hat multiplied could be is 0.25, which would cause you to have the biggest n possible. So if you don't know a prior estimate for your sample proportion, you can use 0.25 as that product. Right here in place of P hat times Q hat. So let's look at a few examples. Example 6 says, suppose a mobile phone company wants to determine the current percentage of customers age 55 plus or 50 plus who use text messaging on their cell phones. How many customers age 50 plus should the company survey in order to be 90% confident that the estimated sample proportion is within 3 percentage points of the true population proportion of customers age 50 plus who use text messaging on their cell phones? So we know that they want the margin of error to be 0.03. That's where they said 3%. And they told us that we want to be 90% confident. So that means that alpha is 1 minus 0.90 or 0.10. And so our alpha divided by 2 is a 0.05. So that z is going to be 1.645 here. So because we don't have a prior estimate, we are going to use the p hat times the q hat of 0.5 times 0.5, our critical z squared, and then our margin of error squared. And that comes out to be 751.7. But remember, we always round up to the next integer for sample size to make sure that we have enough. The 752 customers would be the correct amount. Let's look at another one. Suppose an internet marketing company wants to determine the current percentage of customers who click on ads on their smartphones. How many customers should the company survey in order to be 90% confident that the estimated proportion is within 5 percentage points of the true population proportion of customers who click on ads on their smartphones? So again, because we don't know P hat and Q hat, and we could individually square these, or we could just take the ratio and square them all at once. We're going to use 0.5 times 0.5, and then we need to have our critical z, and this time it's a 90%. So alpha is 1 minus 0.90 or 0.10, and so z alpha divided by 2 then is 0.05. And we already know that z of 0.05 is 1.645. So n is, so z is 1.645 divided by the margin of error, they said was 5 percentage points. And so we always have to turn that percent into a decimal if we want to do something with it mathematically. So that's 0.05, and we're going to square that. And this comes out to be 270.6, but we always round up for sample size. So our sample size should be 271 customers in our sample. Also notice at the end of your notes here, I made one whole page that just the confidence interval formulas for you, and also the sample size formulas for you. So you kind of got them on one page that you can just have handy for as you're working throughout the next lessons and in Alex, and of course for the final exam. Have a great day and catch me back for another video.